Okay, we're in Giancoli Physics, AP edition, 7th edition. We're in chapter 10, fluids, and we're working on general problem number 73 today, so let's jump into that one. That problem reads, a 3.2 Newton force is applied to the plunger of a hypodermic needle. If the diameter of the plunger is 1.3 centimeters and that of the needle is 0.2 millimeters, A, with what force does the fluid leave the needle? And B, what force on the plunger would be needed to push fluid into a vein where the gauge pressure is 75 millimeters of mercury? Answer for the instant just before the fluid starts to move. So go ahead and pause the video, see if you can wrap your brain around that, and come back with a plan. Okay, let's start with identifying the quantities we're working with here. One of the first numbers we see here is a 3.2 Newton force. Now there's another force down here, actually asking us for another force later, so let's call this force 1. It's applied to the plunger hypodermic needle. The diameter of that plunger, so we'll call that diameter. And again, we'll use diameter 1 for the 1.3 centimeters. And then you have a needle with a different diameter. We'll call that diameter 2. Because in part A, they're asking us what force the fluid leaves the needle. That's going to be our F2. That's what they're asking us for. Force number 2. That's what they want to know. Okay, now a subsequent part. What force on the plunger would be needed to push fluid into a vein where the gauge pressure reads a different pressure? Identify that. Let's call this pressure 3 just to distinguish what's happening here. Because when we shift from part A to part 2 here, they're resetting the initial conditions. So they're asking us in part B for a force. That's going to be a force on the plunger. Let's call that force 3. So if we're using the plunger as 1, we'll use the plunger as 3, and then the needle is going to be 2 and 4, just to keep those even. So we just have two different scenarios here. We use these subscripts to keep them straight. So we use subscript 1 and 2 for scenario in A, and subscripts 3 and 4 in scenario B. And just to draw a picture to keep that clear, you've got a needle or a plunger here with a hypodermic needle. Pushing on that thing with a force. And then that narrows down to a needle with a much smaller aperture there. Then we're going to compare these two scenarios. So we can start way back with Bernoulli's equation if you want. This will quickly simplify down, and you can use a easier version. But if you want to start with the core Bernoulli's equation, we'll show you how that simplifies down. Now you notice we're missing a lot of components in this equation. However, we have a hypodermic needle, assuming that the needle is either horizontal or that the height difference is minimal. We can eliminate the height components of this conservation of energy equation in fluids. And then they mentioned they want an answer for just before the fluid starts to move. Once the fluid starts to move, you'll have velocity values here, and because of the different diameters, those will be different. And so we'd have to take that into consideration. But they ask us to calculate just before the fluid starts to move. So this is kind of like when we do dynamics problems, and we assume the sum of forces is 0, even though we're just about to accelerate, but we haven't quite gotten there. We're going to do a similar concept here. We're going to set these velocities to 0, and we're just about to move. And this really just simplifies down to pressure 1 equals pressure 2. It may not look very interesting, but that's okay. So again, we're calling this point 1 over here and this point 2 over here. We're later going to call this 3 and 4 for scenario 2 and part B. And for part 1, we don't have pressure at either location for the question in A, but given that the definition of pressure is force per unit area, and they are talking about forces, and we have geometric dimensions to calculate area, we can replace, again, we're using the equation that pressure is defined as force per unit area. we're going to make that substitution at point 1 and point 2. So that's force 1, area 1 is going to equal force 2, area 2 to get that medicine moving into the vein. Okay. Now for part A, we have F1, and we've got D1, and we've got D2, they want F2. So let's isolate F2. Rearrange that equation. That's going to be F1 times area 2 over area 1. So if you don't actually have area, we'll make the substitution for the area of a circle. Pi radius 2 squared divided by pi radius 1 squared. Now, we don't technically have the radius. We could substitute in the diameters here, but it's easy enough to convert those diameters to radiuses on the fly. They're just cut them in half. It'll be a little easier than tracking a bunch of divided by 2's in here. Now, the pi's do cancel. And so you get the force that you need, or the force of the fluid coming out of the needle is equal to the force of the being applied to the plunger times the ratio of the needle radius squared to the plunger radius squared. So now we're ready to make some value substitutions. Okay. Force 1 is 3.2 newtons on the plunger. Radius 2 of the needle is going to be 0.1 millimeters. And we are squaring that. We can actually, since it's a square over square, we can square the whole ratio. And then the radius 1 of the plunger is going to be half of this, which is 0.65, but when we make that millimeters, it's going to be 6.5 millimeters. Now we are squaring that. That's 1 divided by about 65, which is about 0.02, give or take. When you square that, you're going to get 0.004. Move that decimal over quite a bit. It's going to be a very small number. We'll go ahead and grab our calculators and see what we end up with. Okay, after punching those in, as expected, we get a very small number here. We get approximately 7.574-ish times 10 to the minus 4. Yep. And then minus 4 newtons. And because our significant figures in our problem all appear to be 2, we'll go ahead and round that. Force at 0.2 when you push on that plunger, it's going to be about 7.6 times 10 to the minus 4th newtons. Now that answers part A. Now we need to move on and grab part B. Now in part B, they really haven't changed the overall scenario. We're still talking about pushing this fluid into a vein somewhere. The difference is, rather than giving us the plunger force and asking us for the force at the needle, they're telling us the force of the bloodstream here that we have to push against here. They're basically giving us the pressure on this end now and asking us for the force on the plunger. So it's the same relationship. We just need to rearrange. And they're giving us a pressure at the needle now instead of a force. We're going to have to also go back in and substitute for that. Okay, so we're starting with the same basic initial setup where the pressure on the plunger is going to equal the pressure at the needle. We're resetting the subscripts 3 and 4 here since it's a slightly different scenario. Again, another difference here is we actually have the pressure here, so we don't need to replace that with force per unit area. But we do need to replace pressure 3 with force per unit area because we don't know the pressure there without calculating it. Now they're asking us for the force necessary to push this in. It gives us a pressure here. The area here will be based on the radius of the plunger. So we rearrange that. We get a rearrange this for the force required on the plunger. And I'm also going to take a look at this unit here in a second. We're going to have to convert that as well. But I will go ahead and make this substitution on the area. So the force required at the plunger is going to be pi radius 3 squared times the pressure at the needle. So these are numbers we have or can very easily substitute in. Go ahead and put our numbers in. The radius of 3, the radius at 3, that is the plunger again, which is the 0.065 centimeters. Now in this case, we're working with a pressure. That pressure is in millimeters of mercury, so it's going to be easiest to probably go to pascals, which is SI. So instead of going to millimeters this time, and we don't have a ratio of lengths here, I actually need to calculate this area. We're actually going to use the meter version of this, which would be 0.013. So for us, it can be 0.0065 for the radius. 0.0065 meters. 0.0065 meters. And we're squaring that. That gives us the area. And for pressure of 3, I believe it was 75 millimeters of mercury. Yes. 75 millimeters of mercury, which is one of the more exotic units of pressure. If you convert that to SI, we're going to use either look up on the internet or grab a conversion table for pressures. These are for atmospheres. I want to go into pascals or SI units. And we see here for millimeters of mercury, right there, each millimeter of mercury is worth 133 pascals, newtons per square meter. So it's 1 millimeter of mercury for 133 pascals. So my millimeters of mercury here are in the numerator. So when I get my number 1 here for the conversion, I'm going to put my millimeters of mercury in the denominator here. There's only one of those for every 133 of those pascals. That's a pretty tiny number. It's about 5 times 1,000th. 75 times 100 is going to be 7,500 plus a third more. Call it 10,000. We can move that over 3 is going to be about 10. Plus we're squaring that, so let's move it over another 3. We're talking about 0.01-ish times pi. We're going to get a very small force here. Let's go ahead and grab our calculators and see what we get. Okay, as expected, we got a low number here. Approximately 1.324 newtons. That's a decimal, not a comma. Approximately 1.324 newtons. And again, we're dealing with two significant figures here. We're going to round that off to more appropriate 1.3 newtons. I'll take care of part B for how much pressure, how much force we need to push that into that vein. I'll take care of this problem. Moving on to the next one.